In this video, I'm going to be working through how we can determine how many grams of a particular solute we can dissolve in water using the solubility product constant, KSP. And in this example, we're going to be looking at silver phosphate. And the very first step we're going to be doing is looking at the balanced equilibrium equation of this particular species. So we know that silver phosphate is going to dissolve to form 3 moles of silver ions and 1 mole of phosphate ions. And we can see how these charges neutralize because we have the 3 times the +1 and then 1 times the -3 to give us an overall neutral charge on our undissolved solute. And so the very first thing that we need to keep track of is the phase of each of these species. We know that silver phosphate exists as a solid, and we know that these silver ions are going to be aqueous phase, and we also know that the phosphate ions are going to be aqueous phase. This is important because when we're looking at the equilibrium constants, KEQ, and our solubility product constant, KSP, we neglect solids and liquids because we only care about the aqueous species that have been dissolved by the water. And so in this case, our solubility product constant will be equivalent to the concentration of our silver ions raised to the 3rd power, because we get 3 silver ions per mole of the silver phosphates. And we're also going to multiply this by our phosphate ion concentrations. And that quantity is only raised to the 1st power because we're only generating 1 mole per mole of the silver phosphate that gets dissolved. Now, the next thing we're going to do is make an ice table, and this will tell us the change of the concentration of each of our species. We know that initially I haven't dissolved any silver phosphate into the solution, so there's no silver or phosphate ions present, but per mole of silver phosphate that I dissolve, I will be forming 3 moles of silver ions and 1 mole of phosphate ions. And what we find at the end of this is that we get 0 plus 3x, and x is this unknown quantity because we have yet to determine what is that maximum concentration at which we're going to be realizing a precipitate. So I'm leaving this variable in our equation. And so our final concentration of these species will be 3x and 1x respectively for silver and phosphate. Now, if we plug in these values into this equation, we'll find that our KSP is equal to 3x quantity cubed times 1x quantity to the 1st power. And now looking up the tabulated value of KSP, we can solve for this equation. And doing some algebraic simplification on the right side of this equation, we'll find that 3 raised to the 3rd is equivalent to 27, and we'll have x cubed, and we're going to multiply this by x, and this is equivalent to 27 times x raised to the 4th. This quantity must be equivalent to the left side of our equation, KSP, which was 1.8 times 10 to the -18th. And if we divide both sides by 27, and then raise both sides to the 1/4 power, what we get if we solve for x is 1.61 times 10 raised to the -5. And intuitively, I think of this as the maximum concentration of silver phosphate ions that can be dissolved before we realize a precipitate. Now, with this value, if we wanted to determine how many grams of silver phosphate we can have in 1 liter of water, what we'll do is we'll just multiply 1.61 times 10 to the -5, which is the number of moles you'll have in 1 liter. So I'll just keep track of units. So we'll have moles of Ag3PO4. And we're going to multiply this quantity by 418.6 grams per mole. And what we'll find ultimately is that we can have 6.73 times 10 to the -3 grams, which is equivalent to 6.73 milligrams of silver phosphate. So that is the maximum number of grams you can add to 1 liter of water before you begin to see a precipitate form. And so I hope you guys find it useful. Thanks for watching, and let me know if you have any questions.